This is our next session, and in this session we shall have the esteemed speakers, and they are as follows. Dr. Hitesh Vaidya, he's the moderator of this session, also the chair of this session, former director of Ministry of Urban Development, Chief Technical Advisor, Urban IWF. May I request him to please join us on stage. Also joining us in this session will be Mr. Anshuman, Director, Water Resources Division, the Energy and Resources Institute. Dr. Uday Kelkar, Managing Director and CEO, NJS Engineers India. Ms. Vandana Yadav, Advisor, India EU Water Initiative, GIZ. Mr. Neeraj Gehlawat, Senior Water Resources Specialist, Embassy of Israel in India. And Ms. Kavita Tiwari, Strategic Alliances Division, Office of the Principal Scientific Advisor to Government of India. While we are waiting the esteemed chair and esteemed panelists to join us on stage, I take the pleasure of briefly introducing them all to you. Dr. Hitesh Vaidya is former Director, National Institute of Urban Affairs and Chief Technical Advisor, Urban IWF. Dr. Vaidya is a seasoned urban development expert with over 25 years of experience in policy, project formulation, and project management. He has worked with prominent organizations including UNI Habitat, World Bank, and USAID. We also have with us in this session Mr. Anshuman, Director, Water Resources Division, the Energy and Resources Institute, New Delhi, a seasoned water resources management expert with over 23 years of experience. Also joining us for this session will be Dr. Uday Kelkar, Managing Director and CEO, NJS Engineers India. He's a distinguished water and wastewater expert with 29 plus years of experience in designing water and wastewater treatment projects globally. Mr. Neeraj Gehlawat is a Senior Water Resources Specialist at the Embassy of Israel in India, and he works closely with the Water Attaché, Dr. Lior Asaf, to promote Israel's expertise in water management and technology in India. Ms. Kavita Tiwari is Strategic Alliance Manager, Office of Principal Scientific Advisor to Government of India. She's a seasoned professional with expertise in strategic communication, government affairs, CSR, innovation, and sustainability. Ms. Vandana Yadav is a water management expert with expertise in sustainable water management, project stakeholder management, and remote sensing, and GIS-related modeling. She is currently advising the India EU Water Initiative at GIZ. So this session is a high-level policy dialogue on pathways to decarbonization and net zero energy sector through water circularity. Extend a very warm welcome to the esteemed chair and the panelists who have now taken their seats on the dais. I now request Dr. Vaidya, the esteemed chair, to please take over the session and steer it forward. Maybe you can start by, should we start one by one? Dr. Vaidya here? So we are expecting Dr. Vaidya to join us shortly. Meanwhile, I take the pleasure of requesting Dr. Uday Kelkar, Managing Director and CEO, NGS Engineers India, to kindly share his presentations and also his thoughts.
मेरा भी दे दिया था Very good afternoon to everybody. I was hoping that I'm fourth in line, but it's now I've been brought in to play the start of the innings. So it's got to be very difficult because fast bowls and also game changer can happen. Water and wastewater sector is what I've been working for the last 30 odd years and have got a background for almost 9 or 10 countries, including India and US and everywhere else. When we really look at it, water and wastewater sector, we really don't pay attention to energy and the water combination. It's really a nexus, and I'll walk you through the process. What can be achieved and how can we make it net zero in getting both benefits, getting the water simultaneously, as well as getting net zero as possibility as. Next slide, please. Do I have a clicker? Is this the one? Okay, great, thank you. Oh, if I walk you through, this is got from UN's SDG 6, a standard. I don't want to go much detail, you can get it, but what I like to focus it, the top you see a slide a little bit up there. I like that particular structure. There's a bulb, that's electricity, and there's a water in there going together. So if you really look at it, all the water extraction to all the way wastewater disposal, there is enough amount of energy involved that either created or completely used based on where you are in the system process. If any particular city is looking at how to move in the direction on net zero or carbon neutrality or anything else in that fashion, you can move from left to right. Water supply, supply hydraulics, septage, drainage, point and diffuser pollution, diverse fit-for-purpose sources, and then lastly, adaptive multiple functionalities. And you can literally get, wherever you're moving, an advantage of getting into a higher side of moving slides from water neutrality to energy neutrality and so forth. Over time, it appears to people that, no, I need the water and I need the energy also. How does it matter if I have an expense energy on the account to get a water, because water being a premise that without that I can't live, but with the electricity not having, I can live a little bit longer in the process. But if we combine both of them together, then the advantages are much better, because once you get the water in the process, then that water goes as a wastewater. We have not been looking at very seriously how to develop the water nature so that that wastewater actually becomes a resource for us. And that resource can drive you back and forth in a circular way to get the advantage on the process. This is a 2017 IEA data, which basically walks up the total, the 1,000 watt hours, and on the right side is the percentages, that's the share of the global electricity. I mean, in the earlier session, a lot of people have talked about water energy combination, including hydro energy and usage of energy. And I think Dr. Narula has also talked about various levels of availability of energy and use of energy, or consumption of energy, to be correctly. So if you look at it, transfer, that is pumping, whether it's a groundwater, long-term water, or coming from a long distance. In India particularly, over the last several years, we've been looking at, can I get the water from 20 kilometers, 100 kilometers, 200 kilometers, rather than focusing on whether I can use this wastewater that is generated in the city for development of various amounts of water quality for fit for use purposes and so forth. So if you look at the water as a one concept, maybe it's rainwater, maybe it's groundwater, maybe it's surface water, maybe it's wastewater. So many areas you can look at it, but if you consider that as a one water concept, then that one water concept can take you more deeper into energy conservation, into possibilities of using energy in various aspects and so forth. So if you look at it, reuse then becomes a primary driver in analyzing how to get maximum benefit of the system. You can start from the left side, water supply, dams, intake, hydropower, environmental flows, that E-flows, irrigation outfall, resource recovery, and so forth. And essentially everywhere, if you look at it, each single item of that, it's also heavy energy consumption. If that heavy energy consumption can be optimized and mitigated, then you can get much better benefits in the process. Being a background on wastewater, being a background on processes, if you really want to look at it, the GHG emissions and any other emissions that are coming from wastewater side, because water really doesn't give you GHG emissions, but what it does is uses electricity that is either generated from fossil fuels or generated from natural, either a sunlight or solar and so forth, but the percentage of that use is much lesser. But if you look at the wastewater side, it consumes higher amount of energy as we are moving from just discharge of BOD, that is biochemical oxygen demand, and suspended solids, to the removal of nitrogen and phosphorus. As you move into a lower and lower values of nitrogen phosphorus in the discharge standards, you start to get more and more energy requirement. Just for an example, when you do a normal BOD discharge of say 30 milligram per liter from a 210 or 180 milligram per liter influent, then your energy consumption is hardly 1.2, 1.3 kg of oxygen per kg of BOD derived, or kg of BOD discharged. If you look at nitrogen, to convert from nitrogen to nitrate to denitrate and so forth, then you are actually going to get almost 4.5 times kg of oxygen required per kg of nitrogen consumed or nitrogen oxidized. If you consider that transformation, then obviously you can see the amount of energy that is being used in the process. If you look at the screen-wise, if you go from left to right, you have a raw sewage, so it is pumping, that gets you energy right there. If you have grit removal, it generates odor, so there is an energy utilized, whether it's a gravity or a mechanized system. Then you have an aeration. In normal wastewater plants, 45 to 55% of your energy is consumed in that particular channel or that particular tank, if I may say, because it requires an additional amount of oxygen transfer from bottom of the tank to upside, and the maximum you can drive is about 4.5 meter depth. But the delivery or the transfer efficiency in a conventional aeration system is hardly 30%. So now there are newer technologies are being developed called, say, for example, MABR, membrane aerated bioreactor, which transfers the energy directly from a membrane surface to surface into the liquid side to the tune of almost 70 to 75%. So your drivers for oxygen delivery, so your blower size, your pipe size, and your tankage size is smaller, so you can generate less or use lesser amount of energy to do that. The next one that comes is filtration, and you discharge it. We were doing up to that point fairly well. Once we start looking at it, what else we can do with that, Then that last column of the water is basically started to look at it recycle, reuse, or fit for purpose recycle, reuse. Then you can use it for a variety of application, including agriculture to indirect potable reuse to potable reuse. And then the sludge that comes out, or the biosolids that comes out, can give you a lot of input into your nutrient recovery, into your nitrogen recovery, into your CNG. In the old times, we were doing flaring, so we were going to also burn it out so those CNG can also increase there. But if you convert the methane, which has got a highest conversion rate or highest control rate compared to CO2, or even nitrous oxides has a highest rate, almost 200 times more than the CO2 or CO in the atmosphere to control the GHG emissions, then it's better to utilize them in the process for recycle and reuse. Overall, in the system, that if you look at it, if we mandate these 9 steps in the process of energy efficiency, carbon footprint, cost efficiency, plant capacity, resource efficiency, hazardous substances, whether we need to look at it in terms of, for example, pharmaceutical and PHS or polyhydrocarbons and anything else. And the last one is a little bit tricky, that's PFAS. We don't have a regulation yet in India on PFAS, but we have a regulation now in West, especially in UK and US. If that comes down to us, then our water will require more energy to remove PFAS from the concentration of drinking water. And what standards it can set can also have an energy consumption that you look at. Health, water reuse, and regulatory compliance are the main key 9 points that you need to drive in the process. To me, if we start looking at one water concept in the mindset, then I think we can start considering water as a factory, wastewater as a generation of water factory, not necessarily a tool to provide discharge into the rivers or tools into discharge into the processes. So instead of saying treated wastewater, I would like to say treated used water so that I can convey back, because public awareness and mindset is most important. I'll give you a classical example. When the initially direct potable reuse was started working in West, somebody came up with the idea, it's an election year, and somebody says, I don't want toilet to tap. The whole project just went straight down the link. That given so, if you are really desperate about water, then you can go to Namibia, which is at Windhoek wastewater plant, which is operating for the last 50 years. It literally takes wastewater coming from their households, treats it to a drinking level, and sends it back to the houses. So you need to look at that particular scenario wherever you can in the process. So if I say this, I should see use streams giving me a value stream in the process and generating revenue, generating nutrient factory, and generating energy. I'll give you another example that we've been working with NMCG, National Mission for Clean Ganga, as well as NRCD and the Japanese Bank and the World Bank, to showcase how the wastewater, particularly the biosolids, can be used for a variety of applications. A lot of areas in Indian, particularly agriculture side, we are deprived of carbon. That particular carbon, if it is treated in a fair manner with zero amount or very fine amount of bacterial contaminants, then that carbon can be utilized very effectively as a solid stabilizer in the process. Give you a few examples, what we have done recently. If you see on the left side, if you optimize the treatment process where you can get lesser amount of energy.
After taking a 3 door के पास
यहाँ
कॉपी
चारों फ्लोर पर घुमाया हूँ ये सब बात है.
So if you look at it, this is the plant in Bangalore, funded through Japanese bank, funding through bank. We were looking at optimizing nitrogen in the process so that we can consider what is called as MLE, modified Litzberg process. Not going to get into the details of design, but we can save energy from there, get a much better biosolid that can be thickened, dewatered, and put it back into the digestion process, generate energy, generate CNG, for which the buses can be run or even bottled up and given outside. We've not yet done anything with phosphorus recovery yet, which is also another way. Instead of creating the chemical fertilizer as a phosphorus base, we can create phosphorus from this palletized, and I'll show you pictures. While I was in US, I've done this type of projects there. On the right-hand side, This is, if you get opportunity, do visit this plant in Delhi. This is the largest plant in Asia now, 564,000 meter cube per day. To contain energy, to contain proper analysis, to have a best available sludge, and all these details can be seen in this particular plant. The plant is now completed and trial runs are on. It's got who's who in engineering brought in from the existing as well as advanced technologies to showcase how much water can be reused, how much sludge can be reused, energy can be contained, and also looking at balancing between chemical usages as well as some other techniques. For example, when we did this project assessment, we said we don't want to use chlorine cylinders there, chlorine as a disinfection going into the final version, and said if you give, because of the large size, at one time of a day you can use 90 gas cylinders. And there is a hospital literally next door of that compound, so it's a very high-risk area. So we suggested, it was well defined by the client, accepted, including NMCG and Delhi Jal Board, so we have a largest UV plant there to have a disinfection at a higher rate. If you look at the left side, so essentially you're trying to balance the microbial risk as well as the disinfection risk while looking at the consumption, while looking at usage of chemicals, while looking at what's the best for health analysis and so forth. In the middle one, this is a typical mixer, which is called as Invent mixer, generated in Germany. The mixer uses literally very low power and swings around slowly so that you don't get a full harsh mixing, but a very gentle mixing. So that's the way you need to look at it. Lower energy consuming, higher potential equipment, and so forth. And lastly, which is being done recently in last about 5 to 6 years, because everybody is moving into nitrogen removal, to the process that you can take the nitrogen out of your system. If you go from the left, ammonia to nitrose, to nitrite, and to nitrogen out, it typically takes about 1.8 to 2.7 kWh per hour per kilogram of nitrogen converted to nitrification, denitrification. But there is a process that has been created, formed, and has been used, is to use from ammonia directly to nitrite and straight to nitrogen. That saves significant amount of energy, that saves significant amount. Why this has happened? Because this was done in analysis-wise processes and also optimization of the systems. If you look at wastewater for reuse, and if you start to work on the ladder from irrigation to restricted use, the cost goes up for making the water much better, but is also decreasing review cost. This is the sludge that we have done for analysis and considering. This is the published book for NMCG on how do we do sludges in India for best operation. I think 1 or 2 slides left. This is the data that we did for the Jal Board's analysis at that time, is what else we can create from this sludge. We can get vehicles for CNG, we can get industry fuel, we can get agriculture use, we can get industry, or we can use torrefaction, and we've given number of tons of this sludge to NTPC to see if they can save their coal, and they use this one. It really worked well, because as long as there is a water, there is a wastewater, there will be a sludge. And if this can work out also, this can also provide. This was a pilot done in the process. This is the palletization in forming phosphorus into the process, into the system. This is the recycled reuse. This is the worldwide data showing how it has moved from different water sources to IPR to DPR. Let me go on the last slide. This is what I would like to take you guys away from, and the end of the process is you need to have 3 focuses. Focus 1, 2, and 3. 1 should be adopt new design and engineering practices and optimize energy use to develop asset management capacity and O&M optimization in the bid document. So we don't have to reject if there is a new technology available, data available worldwide. Doesn't need to happen only in India, it can happen anywhere, because wastewater management treatment is same everywhere else. Focus 2, continue to develop excellence in digital data, because more the data you have available, more planning you can do, and AI/ML through develop process optimization. And the last, focus 3, start putting some amount in your piloting. If you do piloting very well, you can get optimization data, you can do a lot of recycle reuse, you can allocate your percentage of cost into the process, and then you can move to a higher level for energy conservation, and we can have lesser and lesser amount of energy available or generated energy through your wastewater plants. And that's it. I'd like to conclude. Thank you very much for your time. I thought I was going to conduct so I can take a lot of time.
Thank you, Dr. Kelkar. Ladies and gentlemen, we have just been joined by Dr. Hitesh Vaidya, the esteemed moderator and the chair for this session, so a warm welcome to you. Meanwhile, we move on to Mr. Anshuman, Director, Water Resources Division, the Energy and Resources Institute. May I request him to kindly share his presentation.
Thank you, Chair, and of course, India Water Foundation, Dr. Arvind, for this opportunity. It's been almost 20, 30 years that as Terry and as person in this field have been learning into how to look into this challenge, water and energy. There's a fair bit of experience, and I think we all know that when you talk about consumption of water, we need energy, and both ways, generating energy, we need water, and water, to transport, we need energy. Quite well known. What I'll try and do is look into some of those examples from agri, domestic, and industrial sectors that we have worked over the last 3-4 decades as Terry, and share our experiences. Now, what I'm going to do is, and I think thanks to Dr. Kelkar, that he at least, in a way, given a perspective of what can be done with, he talked about wastewater though, but with by and large the energy and water sector, there's a lot of opportunity, and I want to share with you some of those, something that we have driven and facilitated, moving forward. There are a lot of challenges, and I don't want to talk about them, but I think in terms of moving ahead, what we need to do is we need to look into the sustainable consumption and production of water, and in every sector, agriculture, domestic, and industrial. Rather 2 or 3 major areas, resource recovery, reducing the wastages, improving the efficiency and productivity, and of course, conservation. And all of these are very closely linked. We all have talked about, water, energy, food, ecosystem, and so on and so forth, nexuses. Let's take a look at where the opportunity and how do we drive them on ground. And I'm giving you some of the examples, which we have driven through our projects. So let's start with the agriculture sector. There's a project in Punjab, some of you might be knowing, it's called Pani Bachao Paisa Kamao. It's the government of Punjab which is running it. And along with the World Bank and other partners, we have driven some of these interventions. The idea was to look into what are those, this is basically direct benefit transfer of energy. The idea was to look into what are those interventions that the farmers on ground can adopt to not only, save water from the ground, because that's a challenge in Punjab, but in the process also save energy. And the idea was to incentivize the farmers by some, unit amount through the saving of energy and water. But the challenge was that these stakeholders, these farmers, needed to be brought on board with those kind of interventions which are possible. What we did was we went to the location, and amongst all those interventions, as you can see, right from micro irrigation to furrow, laser leveling, mulching, and other short duration rice varieties, for example, DSR, and so on and so forth. We demonstrated all of these on ground to the farmers in the demo farms, and a lot of outreach and capacity building activities involved. And we measured on ground what is the kind of delta change that is going to happen with the processes. So we had this Kharif and a Rabi season and monitored. So I'm giving you some examples, not all, just to give you the perspective. Now, the idea was to demonstrate to the farmers that there is an efficiency factor. If you can use, for example, drip and sprinkler system or a good, resistant variety of rice, and, maybe evaporative losses, saving through, close conveyance and so on and so forth, there could be savings of water. And as I said, we measured. What you can see is some of those examples of, the farmers who had used these interventions. And as you can see, there was a range of around, let's say, 10 to 30% of, water saving in the Kharif season. And there were many feeders in which we had taken up. And what you can see at the bottom is basically the water and energy savings, again, ranging around anywhere between 6 to 30%. And not only that, we also looked into the productivity and efficiency factors. So by and large, the irrigation productivity, the efficiency, overall this was better than the conventional processes. And we also tried to assess what is the kind of overall picture in terms of the carbon saving. And as you can see, there was a fair bit of carbon saved in terms of tons during the period of assessment from 2018 to 21. Now, what I'm trying to emphasize the fact is, we all know that this is a possibility. I think the important part is to onboard the stakeholder on ground by demonstrating and facilitating them in the process. And what this project, in a way, I would say, kind of demonstrated was that not just the technologies and the processes, but also onboarding, comforting, winning the trust of the local community, in this case farmer, through demonstration of the kind of technology and the best practices, looking into the bottlenecks as well, and letting them prioritize what is to be taken on ground, is what the learning was actually. Now, it's not a one-size-fits-all solution, and I'm also not suggesting that this will across the India work. There are learnings in different states. But we were discussing yesterday in the India Water Impact Summit that I think the challenge, or maybe the solution to the water sector, is we have to customize the solution locally in each of the states, in each of the districts, as far as possible, as best as possible. So I just wanted to give you that example, just another example of one technology that we have come across with, is part of the DST project. It's called OptiFlow. Not going into detail of this, but just to share with you, in any transmission loss, in transmission of water, we have this variation of around 8 to 15% of pressure variation, because of which we have losses of both energy and water. What we have done, we have developed this particular valve, which basically reduces this, makes this pressure constant and brings it down to less than 2%. So that difference is basically the saving of energy and water. We have demonstrated this on ground. This is ready for, it's already being commercialized now. Anywhere between 10 to 12% is of both water and energy saving in different dimensions. And you can apply this not only in the irrigation sector, but also domestic sector. Now I want to come to the energy sector. The largest consumption of water in the energy sector is thermal power plants, which generates energy for us. I'll give you an example. We have just completed a project on benchmarking industrial water use efficiency in India. And there's a